In automotive coatings, one of the most common challenges for RD&I teams is understanding why results obtained on laboratory spray panels often differ from those observed on full production vehicle bodies. This discrepancy is not due to error in formulation, but arises from fundamental differences in geometry, airflow, thermal mass, and process variability between controlled lab conditions and real-world production lines. Geometry is a key factor. Laboratory panels are flat or simple curved substrates, which promote uniform coating flow, solvent evaporation, and metallic orientation. In contrast, production car bodies feature complex three-dimensional surfaces, deep recesses, sharp edges, and large, continuous panels. These features create local variations in wet film thickness, air movement, and solvent evaporation rates, resulting in differences in flow, leveling, and appearance effects, such as mottling or metallic flop. Airflow and oven dynamics also play a critical role. Spray booths and curing ovens in production lines introduce variable air velocities, turbulence, and temperature gradients that interact with a coating's rheology evolution and solvent evaporation kinetics. On a lab panel, conditions are highly uniform, allowing idealized drying and cross-linking behavior, whereas on a production body, these variations can generate uneven film formation, increased risk of runs, sags, or solvent popping. Thermal mass and orientation further contribute to observed differences. Production panels are larger and more massive than lab coupons, which affects heat transfer during flash-off and curing cycles. Similarly, the orientation of the panel, vertical, horizontal, or inclined, modulates flow behavior and solvent evaporation. These factors influence the final metallic particle orientation, gloss development, and defect incidence, especially in solvent-based primers, basecoats, and clearcoats. Laboratory-to-line translation is also affected by process variability. Variables such as spray gun distance, atomization pressure, line speed, ambient humidity, and solvent blend interact with the coating's inherent properties to magnify minor deviations, often resulting in OEM validation failures that were not predicted by lab tests. RD&I engineers must anticipate these differences by designing test panels that replicate critical production parameters, using representative geometries, airflow simulations, and environmental conditions. From a practical standpoint, lab panels remain invaluable for formulation development, color approval, and defect screening, but their results must be interpreted in the context of full-scale production bodies. Understanding the underlying physics of solvent evaporation, rheology evolution, and metallic orientation enables engineers to predict, mitigate, and control deviations between lab and line. In summary, differences between lab panels and production car bodies arise from geometry, airflow, thermal mass, orientation, and process variability, all of which influence solvent evaporation, rheology, metallic orientation, and defect formation. Successful RD&I decision-making depends on recognizing these factors and designing tests that bridge the lab-to-line translation. If you have questions about lab-to-line discrepancies, production validation strategies, or coating defect mitigation, submit them in the comments for discussion in future episodes.